In this video, we'll find the deformation of a tapered bar of rectangular cross section. It means the bar is tapered. One end is the bigger end, and the cross section area goes on decreases. The other end is smaller end. So this is the tapered bar with rectangular cross section. If you see here, the cross section is rectangular. If you see this one is thickness and this one is the width here. So in the previous video we discussed the deformation of a round bar. Whatever the bar is there, the cross section, it will be the diameter, or it is round. But in this we'll derive the deformation of a tapered bar with a rectangular cross section. Okay. First we'll go how the bar is, what are the specifications here. So this is the tapered bar. So one end is, the bigger end is B1 and the smaller end is B2 here. Smaller end is B2. Its length is, the tapered bar length is L. Okay. And it is subjected to the axial tensile load. Axial tensile load P. That is P here and P here. The thickness of the bar is T. The thickness of the bar is T. It means the one end is B1, the smaller end is B2, the length is L, thickness is T, and it is subjected to the axial tensile load P. Okay. So we'll start with the data here. First, consider a tapered bar of rectangular cross section as shown in figure. Okay. Let B1 equal to, what is B1? It is the width at the bigger end. Width at bigger end. B2 equal to width at smaller end. Okay. Next, L. What is the L here? L equal to length of the bar. L equal to length of the bar. Okay. What is P here? P equal to applied axial tensile load. Because it is along the axis, so it is tensile. Nature is tensile, so it is called applied axial tensile load. Okay. And what is the T here? T is equal to thickness of the bar. Thickness of bar. Okay, it is constant because here the T is constant, the T is constant here. Only the width is, it is varied here. That is, goes on decreases here. Okay. Now we need to consider a small element. This element is at a distance of x. At a distance of x from the bigger end. And the length of this element is how much? It is dx. It is dx. The width of the element is how much? It is b suffix x. First we need to, after considering this small element, we need to derive the deformation of this element. We need to derive the deformation of this element. Later, if you integrate from 0 to L, because the bar is having the length, it starts from 0 to L. If you integrate with this to this element, the deformation, then we'll get the deformation of the whole tapered bar. Okay. So now consider an element and is at a distance of x from the big end. Okay, from the big end. Dx is what? Let dx equal to the length of element And what about bx? B suffix x equal to the width of element. Okay, these are all the datas related to the given bar. Now we will derive the deformation with respect to this element first. Okay, the deformation of element equal to, okay, just I'll take deformation del L suffix x because it is the element here. What is the formula for deformation? The normal formula, general formula is PL by AE. PL by AE. That is normal PL by AE. Okay. Where P is applied load, L is length of the element or length of the bar, whatever it may be, and A is cross section area, and E is Young's modulus. This is the normal general formula. If you consider this formula to the element, how this will becomes? P is applied load as usual. This is P. What is L here? L is length of the element. L is length of the element. It is dx. That is dx divided by area. That is area of the element. It is, I'm just A suffix x. Area of this element. I'm considering this. Then Young's modulus is constant. Okay. So this is the formula for the element, the deformation. Now P, you know, dx already length is there, E is constant for the element or the bar. Now we need to consider the area of the element, because area is, it is not constant because the area will be goes on decreases. So we need to find out the area. Area of element equal to, what is normal formula for rectangular cross section? Width into thickness, right? Width into thickness. That is, what is the width? Width of the strip is bx. That is width. Thickness is how much? T. Because thickness is constant. Thickness is constant anywhere. Into thickness. Okay. This is area. So now if you want, what is bx? I want the width of the element in terms of B1 and B2. In terms of B1 and B2. Now I will find out bx, width of the element in terms of B1 and B2 equal to, first this is width of the element, this minus something is there, that is B1 minus or something, B1 minus, that is B1 minus B2, whatever B1 minus B2 upon length divided by length into x. This we are already explained in the previous derivation while solving the deformation of a tapered bar of round cross section. The same you need to apply here also with rectangular cross section. Okay, once again I'll explain here. This width is nothing but B1, because here bigger end minus something, because here something is there, minus B1 minus B2, whatever you are getting, B1 minus B2 divided by total length into x, whatever the x is there, that is x along the x here. Okay, this is bx. This will be equal to B1 minus, for simplicity I will write this one as k into x, where what is k? K equal to B1 minus B2 divided by L. Okay, only for simplicity purpose I just substituted k. Okay, k equal to B1 minus B2 divided by L here. So this is the width of the element. Now once if you find out the width, where we need to go? Area of the element here. Then what is the area? Therefore area of the element Ax equal to, what is the width of the element here? Width of the element is B1 minus Kx. This is the width into thickness. this is the area of the element, whatever you are finding. This is the width, this is the width, and this is the thickness. Width is in terms of B1 and B2. B1 and B2 here. Okay. Now, if you find out the area of the element, where we need to go? You need to find out the deformation, because deformation is in terms of area, divided by area is there here, right? This I'll call it as equation A. Equation A. Okay. Therefore, equation A becomes deformation of the elemental strip equal to P into dx divided by, what is the area of the element? Substitute this one, area of the element, that is B1 minus kx into T into thickness. So this is the deformation of the elemental strip. Now we need to find out the deformation of the whole bar. If you want deformation of the whole bar, you need to integrate, right? Integrate 0 to L. The length of the bar is L. Okay. The next step is you need to find out the deformation of the bar. Therefore, deformation of bar equal to whole bar. This is dl equal to integration of 0 to L. 0 to L. 0 to L, that is deformation of small element, right? Deformation of the small element. How we will find out? This will be 0 to L. What is the deformation of the small element? P into dx divided by B1 minus k into x into T here. Okay. So this is the deformation. Now you need to T into E, that is you have E also here before. Okay. Because PL by AE, whatever before the formula is there, PL by AE. Next, PL, and this is the area and this is the Young's modulus. Okay. This is T into E here. Okay. This is T into E. So that's why here E also comes. PL by AE. Only we calculated the area here. Now this will be equal to, what are the constants? You just remove it. P divided by T into E, integration of 0 to L, that is 1 divided by B1 minus k into x. This is dx. Okay. Next, P divided by thickness into Young's modulus. Okay. Now you need to integrate. You need to integrate this one. That is 1 divided by B1 minus kx into dx is log to the base E, that is B1 minus kx. This is this integration into integration of the inside part, that is minus 1 divided by k you will get. Okay. This is 0 to L. Okay. This I'll write this one as, did you get the integration here? Because 1 divided by B1 minus kx, the integration of 1 divided by B1 minus kx is log to the base E B1 minus kx into integration of inner part, that is minus 1 divided by k. Okay. Now again, for take k outside here, because k is constant, that is P divided by T into E into k, that is minus log to the base E into B1 minus k into x, that is 0 to L. 0 to L here. Okay. This is deformation of the bar. Now again, simplify this one. Substitute k value, because for before we took, what is the k? K equal to B1 minus B2 divided by L. Okay. That you need to substitute now. Okay. Therefore, deformation of L equal to P divided by T into E into k. Now minus log to the base e, that is b1 minus, what is k? K is b1 minus b2 divided by L into x. This is 0 to L here. Did you get the point? That is, only I substituted k value here. K is b1 minus b2 divided by L into x here. Now, substitute upper and lower limit. Substitute upper and lower limit. This dl equal to p divided by t into e into k. Now, first upper limit I will substitute minus log to the base e, that is b1 minus b1 minus b2 divided by L into L, upper limit. Okay, so minus, now substitute lower limit, that is minus log to the base e, only b1 you will get, because here substitute the x equal to 0, the x value is 0, this will becomes whole 0, therefore only b1 will get, that is minus log to the base e, it is b1. Okay, first substitute upper limit is here x, whatever you are saying, that I substituted minus log to the base e, b1 minus b2 divided by L into L, that is the upper limit, minus, next the lower limit is here I am substituting b1, because here if substitute the 0, this term becomes 0 here. Okay, this is the after substitution. Now cancel this L will be cancels here. Okay, what will be the remaining term here? dl equal to p divided by t into e into k. Now minus log to the base e, this b1 minus b1, this cancels, right? This b1 cancels, and this becomes, that is log to the base, that is minus into minus plus, that is log to the base e b2, that is log to the base e, this is b2, right? This minus into minus, it will plus log to the base e b2. Now come to this. So this is minus into minus plus, right? Minus into minus plus. So that's why this is as usual b2, this is plus, but this will becomes minus here, right? Because minus as usual log e, this is minus into minus plus b2 plus b2. Now come to this one, minus into minus plus, here log to the base e, this is b1. Okay. Now this I can write, this I'll write it as p divided by t into e into k. I'll just shift here the terms here, log to the base e b1 minus log to the base e b2. Okay, next p divided by thickness into Young's modulus into k. Then can I write it this one as log to the base e b1 by b2, right? b1 by b2, I can write this one, right? Okay. Next, substitute k value here also. Okay, now you can substitute k value, because what is the k value here? K is b1 minus b2 divided by L. Now this I will substitute, that is deformation of the bar dl equal to p divided by t into e into b1 minus b2 divided by L, right? Divided by L into log to the base e b1 by b2, okay. So now finally I'll write this one as PL by AE in the form of PL by AE. How to remember? Just take, I'll write this one PL AE. This is E, right? E as usual Young's modulus. How will remember A? A is, that is the width into thickness, right? Width into thickness. How we will write the width here? That is B1 minus B2 divided by, I will take in the denominator here, log to the base E B1 by B2 into thickness here. Okay, that is deformation. Just I'll tell how to remember deformation. PL by AE, normal formula. P is as usual, applied load. L is the length of the bar. A of the tapered rectangular bar is B1 minus B2, that is width into thickness, right? Width into thickness. But thickness is same. Width is B1 minus B2, how much is there? Divided by log to the base E B1 by B2. This is width. Okay? This is how you need to remember the formula here. Are you getting my point? Okay. So this is the formula for finding out of the deformation of a tapered bar with rectangular cross section subjected to the axial tensile load. Okay.